Hi everyone, my name is Deepthi Raghunandan, and I will be presenting Code Evolution, Understanding How People Change Data Science Notebooks Over Time. This work was achieved in collaboration with Aayushi Roy, Shenzhi Shi, Niklas Elmqvist, and Leilani Battle. In this presentation, I want to show you our unique approach to unfolding computational notebook archives to understand how data scientists iteratively derive insights from their data. I will show that notebook characteristics, like number of code cells, can point to the type of analytical activity a data scientist is engaged in. That we can automatically track these characteristics to track analysis activity. That changes in these notebook characteristics can also be tracked across notebook archives, and that these changes can also point to analytical iteration. Here's an example of a Jupyter notebook document made publicly available on GitHub. The author of this notebook has developed a computer vision model to automatically detect American Sign Language from a dataset containing images of 24 static hand shapes corresponding to the English letters. We can see that this data scientist has a good idea of their analytical objectives, but iteratively explore their data to establish a process. They choose to communicate a lot of their process to establish credibility for their independent class assignment. We also notice that sometimes the notebook author removes alternative explorations while, for example, choosing between different methods for converting images to grayscale. This author chooses to track this part of their process via GitHub, but doesn't communicate about it in favor of a more cohesive narrative for their audience. Qualitative studies from this conference, like Exploration Explanation in Computational Notebooks by Adam Rule et al., or What's Wrong with Computational Notebooks by Chattopadhyay et al., or The Story in the Notebook by Mary Beth Carey et al., establish more than a few reasons why explaining an iterative process with a notebook is easier said than done. Despite these constraints, a recent Kaggle survey shows that computational notebook platforms like Jupyter Notebook or Jupyter Hub are the most popular development environments for data scientists. So we set out to better support the management of process-related details using notebooks. To do this, we needed a way to map notebook interactions to analysis activity, and we needed a data set that could help us observe how data scientists interact with notebooks. Most of the previous studies on data analysis in notebooks have been smaller in scale and qualitative. We decided to operationalize these findings with quantitative methods and take advantage of notebook versioned on GitHub as a means to observe analytical process. We found 4.7 million notebooks on GitHub and chose to randomly sample a total of 400,000 of these. Through our own exploratory analysis of these notebooks and their versions, we realized that not all notebooks are data science oriented, contain enough versions for observation, or contain original work. So we identified 3 different filtering mechanisms. First, to ensure that notebooks in our corpora were data science oriented, we eliminated notebooks that did not invoke or use at least 2 popular data science libraries. Second, to ensure that we could observe substantive changes to notebooks within versions, we eliminated notebooks with fewer than 4 commits. Third, to ensure that we were observing unique changes in notebook versions, we eliminated notebooks that were not changed by the repository owner. We were able to select a total of 2,574 notebooks after applying these filters. Now that we had a corpora of data science notebooks and their versions, we set out to establish some quantitative methods to understand data analysis in notebooks. We generated a rubric that mapped previous findings on notebook characteristics to analytical activity, such as data exploration and communication. We designated a score called Exploration Explanation Score, EE score for short, for each stage of the analysis process. The smallest score, 0.1, indicated data exploration. The largest score, 1.0, indicated communication. Notebooks in categories below 0.6 demonstrated messy iterative analysis with little explanation or narrative. Authors of notebooks in categories above 0.5 made attempts to explain their steps, their insights, and/or their motivations. These notebooks told a clear story to a wider audience. We iteratively tested and adjusted the boundary condition of our rubric based on a sample of 244 notebooks from our corpus. This meant applying EE scores to 244 notebooks. For example, if we scored the notebook we saw earlier, we would first read the notebook to understand what the author was attempting, examine how well the notebook was organized, look for the completeness of their analysis and indications of dead-end iterations, and then look for explanatory elements like visualizations and headers and text. We would try and categorize text to see whether the author was documenting their process, annotating their insights, or establishing their motivation. We would give this notebook a score of 0.7 based on the rubric. We used our scored sample as a ground truth to automate scoring of all notebooks in our corpora. First, we needed to identify and extract notebook metrics that could map to the EE scores. We found that organizational and output-related characteristics were the most correlated. We extracted things like number of markdown cells, spacing in markdown cells, number of code cells, and the number and types of visualizations. We fitted a linear regression model. The scatter plot you see shows how the linear regression model predicts scores based on notebook characteristics on the x-axis and manually assigns scores on the y-axis. The R value of this regression was 0.591. This statistically significant R value affirms that we can automatically map notebook metrics to a spectrum of exploratory explanatory behaviors. Since analysis is an inherently iterative activity, we wanted to figure out if we can detect iteration using changes in notebook metrics as a guide. To find this, we constructed a time series dataset with 2,574 notebook versions. Then we automatically scored each version with the linear regression model from the previous part. We grouped notebooks based on the first and last scores in their series. For example, notebooks that started with exploratory scores and ended with explanatory scores were labeled exploratory explanatory. Then we sampled and qualitatively observed the changes that led to shifts in scores in each group. Based on this analysis, we realized that GitHub commits can capture edit behavior and that these map to authors' analysis behavior. Thus, our results support the idea that we can automatically detect a variety of analysis activity and iteration across computational notebook versions. A lot of our findings were consistent with previous work, and this further validates our methods. Here are our notebook groups. The red lines indicate the general trend of EE scores within each group. We found that a variety of shifts along the exploratory explanatory spectrum were previously unobserved, actually. For example, we observed shifts away from explanation towards exploration. We speculate that this behavior demonstrates the beginning of a new sense-making iteration. Second, some notebooks have yet to reach the explanatory stage, or may never will. We believe that this suggests that authors are content to keep certain analysis exploratory. In this presentation, I showed you our unique approach to understanding how data scientists iteratively derive insights from their data. That notebook characteristics, like number of code cells, can point to the type of analytical activity, that we can automatically track these characteristics to track analysis activity. And that changes in notebook characteristics can be tracked across notebook archives, that changes across versions point to analytical iteration. With these findings, we have now enabled the direct application of these methods towards building adaptive data science tools. We believe that our findings can motivate a lot of different types of design changes to data science tools. But here, I will just discuss one. We learned a lot about how individuals work with data and what this looks like in notebooks via notebook metrics. But this is all for naught if we can't empower our notebook author with this information. Going back to our example, a platform that could automatically detect that our author was choosing between pre-processing methods could also understand that the author was engaging in iterative goal-oriented data analysis. This information could be made available as part of a live notebook environment. Interactive visualizations of their notebook meta-analysis could help our author reflect on the methods they've already tried. Our author could even choose to compile this information as part of a class presentation. We're excited to see that this is the direction our community is headed in, and we hope that our work contributes to their success. A final thank you for all those who supported this work.